Hello and welcome to the lecture on greedy algorithms. I will be introducing this topic using a number of examples, including the classical knapsack problem. Once we understand how the greedy approach works, we will look at how it differs from dynamic programming studied earlier. We will then solve two more problems, namely the activity selection problem and Huffman coding using greedy approaches. A more comprehensive explanation on this topic is given in Chapter 16 of your book. First, a recap. So, what was dynamic programming, or DP? In our previous video, we saw that DP is an approach used to find an optimal solution to problems in which subproblems have an optimal substructure. As a result, the optimal solutions to the subproblems would guarantee that the solution to the original problem is also optimal. In contrast to divide and conquer, DP avoids solving subproblems more than once by storing the solutions to already solved subproblems in a table and reusing these solutions whenever the same subproblem is encountered again. Therefore, by using additional memory used to store the table, DP speeds up the problem-solving process, making it faster than divide and conquer approach. Recall that in divide and conquer, same subproblems are computed redundantly as there is no lookup table. We saw three examples that were solved using DP approach: the rod cutting problem, the matrix chain multiplication, and the longest common subsequence problem. As we all know now, DP uses memoization to avoid redundant calculations in either the bottom-up or top-down manner. In spite of the fact that DP always returns an optimal solution, it is exhaustive as it has to solve the subproblems that have the same structure as the original problem. In other words, DP returns the global optimal solution, but to do so, it takes a longer time to find the optimal solution. So, is there any other way by which we can get a near optimal solution much faster? The answer is yes, and that is using greedy algorithms. By this approach, the best choice at that very moment is made, which may or may not eventually lead to the final optimal solution. This means that the decision made at a very particular moment is based on local information and not global information of the system. To see what I mean, let's look at the very simple example of making changes using the minimum number of coins. Let us assume that we have four types of coins: 10, 50, 100, and 500 tenge. We want to use the minimum number of coins that would sum up to 1,380 tenge. The strategy that first comes to mind is to start with the highest valued coins, that is, use as many 500 tenge coins as possible. So we can use maximum 2 500 tenge coins to give us 1,000 tenge. Next, we use 300 tenge coins to give us 1,300 tenge in total. Then we use one 50 tenge coin and three 10 tenge coins to give us a total of 1,380 tenges. The strategy we used here is what we call greedy, because we choose the maximum values that are feasible at each step. The question is, does the greedy approach always guarantee optimal solution? And the answer is no, it does not always work. So, in this example, the greedy approach resulted in the best solution. But using greedy does not always guarantee to yield the best possible solution, or what we call the global optimal solution. In algorithms, the knapsack problem is a very famous example with lots of applications in various fields. Let's first see what is the knapsack problem and then explain its variants. Suppose there is a thief who has a bag that can carry the weight of W kilograms at most. The thief breaks into an antique shop and wants to take as many items as possible that worth a lot. So each item in the shop has a weight and a price. The knapsack problem is taking as many items as possible so as to maximize the price value of the items taken without overloading the bag. To exemplify the knapsack problem, assume the bag can carry a maximum weight no more than 50 kgs. And there are 3 items with the weights and values as given in this table. A smart thief would first quickly calculate the value by weight for each of the items to have an idea of the value of the items per kg. So this calculation is done for you and shown in this table as such. So the greedy approach would be as follows. First, calculate the value to weight ratio of each item. Second, take the item with the highest ratio value. In this example, it would be item 1, which has the ratio value of 6. So the bag can still accommodate 40 more kgs. Third, select the next item in line, which would be item 2, with a ratio value of 5. This leaves us with 20 more kgs to carry. Since the third item weighs more than 20 kgs and exceeds the maximum load of the bag, it cannot be carried. Therefore, using the greedy approach, the thief can carry 2 items, that is item 1 and item 2, which is worth $160 in total. But is this the optimal solution? What if the thief would have taken items 2 and 3? We see that it would have worth more, that is $220. Now, let's solve the knapsack problem using dynamic programming. Assume we have n items, each with weight Wi and value Vi. We define MIW to denote the maximum value achievable for at most W kgs when selecting up to I items. And here I takes values from 1 to n. So the recursive equation for MIW is as such. For a bag where W is equal to 0 or where there is no item, we would have it equal to 0. This is trivial. Now, if the weight of item I is greater than the weight W, it means that we cannot carry item I, and therefore MIW would be equal to the maximum value of the I minus 1 items already selected. That is MI minus 1 W. Otherwise, if Wi is less than or equal to W, then we have to take the maximum of Mi minus 1W and Mi minus 1W minus Wi plus the value of item I. Let's use this recursive equation in our example. This is the table we had earlier, and this is the MIW table that we need to fill up using the recursive DP equation repeated over here. For W is equal to 0, this row would be 0. For W is equal to 10, we see that only item 1 has a weight less than or equal to 10. So the entire row is filled with the value of item 1, which is 60. For W is equal to 20, we see that items 1 and 2 have weights less than or equal to 20. But selecting item 2 instead of item 1 would give us a total value of $100, which is more than $60. So M220 would be equal to 100. For W is equal to 30 kgs, M230, that means this, becomes $160, which is calculated by taking the maximum value of M130 according to this recurrence equation, which is 60, and 110 plus V2, which is 60 plus 100, that is $160. So M 2030 would be equal to $160. We do not select item 3 here because its value is lesser than $160. For W is equal to 40, we can take item 1 and 3 together, worth $180 in total. Finally, for W is equal to 50, M350 is equal to maximum value of M250 and M220 plus $120, which is V3. This would give us a total of $220, which is the optimal solution to this problem. This version of the knapsack problem is known as the 0-1 knapsack problem because for each item, the thief must either take it or leave it behind. He cannot take a fractional amount of an item or take an item more than once. Another version of the knapsack problem is known as the fractional knapsack problem, where the setup is the same, but the thief can take fractions of items rather than having to make a binary 0 or 1 choice for each item. So a thief can break up an item into smaller parts and take smaller fractions of it in order to maximize his profit. Part A of the figure corresponds to the 0-1 knapsack problem, where we have the 3 items and their values, and we have the knapsack of 50 kgs. We cannot break up these items, so the best combination would be to take item 2 and item 3, which would give us a total sum of $220. On the right, we have the fractional knapsack problem, where if we take 10 kgs from item 1 and 20 kgs of item 2, it would give us a total of $160. Or if we take 10 kgs of item 1 and 30 kgs of item 3, it would give us a total of $180. But we can get more worth by taking item 1 entirely, which is 10 kgs, then taking item 2 entirely, which is $100, and taking 2/3 of item 3, that is taking 20 kg out of 30 kgs of item 3. So 120 divided by 30 would be 40, and since we are taking 2/3 of it, so we would get an additional profit of $80. So the fractional knapsack problem would give us a more worth value of $240 using the greedy approach. Therefore, to conclude, the greedy approach does not give us the optimal solution in 0-1 knapsack problem, while DP does. But in the fractional knapsack problem, the greedy approach always guarantees the optimal solution. So, the greedy approach to a problem can be compared with its DP counterpart as follows. DP can be said to be a more general strategy than greedy. If a problem can be solved using greedy, it can definitely be solved using DP as well. This is because both approaches share the same concept, where optimal solutions to the original problem include the optimal solutions to the subproblems. However, keep in mind that the vice versa does not necessarily hold. That is, every optimal DP solution also having an optimal greedy solution is not always true. Now let's look at another example and try to solve it using the greedy approach. This problem is called the activity selection problem and is a scheduling problem which is mostly experienced when allocating lecture hours to classrooms. Suppose you have a set S of n activities or lectures, and you have a single resource, say a classroom with proper air conditioning that all professors like. We want to accommodate as many lectures from the set S into this classroom such that no two lectures overlap. To define it more formally, let each activity I have a starting time s of I and a finishing time f of I bounded as such. So every activity I is active in the interval Si to Fi, not including Fi. We say two activities Ai and Aj are compatible if and only if their intervals do not overlap. Or in other words, if Si is greater than equal to Fj or Sj is greater than equal to Fi. Therefore, we want to maximize the number of compatible activities that can be scheduled to use the common resource. Let us assume that the activities are sorted in monotonically increasing order of their finish time and not start time. So they are ordered as shown over here. So we shall see later on the advantage that this assumption provides. So for the set S of 11 activities, we would have such a table where f of i's are ordered in an increasing manner. For this example, the subset A3, A9, and A11 consists of mutually compatible activities. This is a feasible solution, but this is not the best solution, as we have subsets A1, A4, A8, and A11, as well as A2, A4, A9, and A11 that are larger subsets. Now, let us think of a DP solution to this problem, where we need to formulate an optimal substructure for the problem. We define the set Sij, which refers to the set of activities that start after activity Ai finishes and finishes before the start of activity Aj. We now want to find the maximum set of compatible activities in Sij. Let's call that set Aij, which includes some activity Ak in it. So by introducing this arbitrary activity Ak in Aij, we have broken our problem into two subproblems. That is finding compatible activities in subsets Sik and Skj. Let Aik be the intersection of Aij and Sik, and Akj be the intersection of Aij and Skj. In this way, we can say that Aij contains the activities of the subsets Aik and the arbitrary activity Ak and the activities in the subset Akj. So the cardinality or size of set Aij can be defined as the sum of the sizes of the subsets Aik, Akj, and Ak, which is 1. Therefore, the optimal solution for the set Sij, which is the maximum size of the set, is stored in Cij and is given as shown over here. Similar to previous DP examples, we do not know the value of k in the activity Ak. That is, we do not know the optimal point at which we need to divide the set Aij into two subproblems. So we have to check for all possible k values in the set Sij to choose the optimal value. This is reflected by the max function in the recursive equation of the problem shown here. By memoization, we can solve this problem to get the optimal solution. But what if, instead of having two subproblems, we just define the problem in a way that we only solve one subproblem in each step? Is it possible? With having only one subproblem to solve each time, we therefore do not have to worry about finding that optimal k value by exhaustive computations. Thinking about it a bit, we see that it is indeed possible to come up with such a simplified approach. We know that the finishing times of the activities are sorted in an ascending order. All we need to do is to choose an activity that releases the resource so that as many activities that follow can use it. The activity of choice based on this strategy would be A1 in the example. If we behave in a greedy manner, We now have only one remaining subproblem to solve, and that is finding activities that begin as soon as activity A1 finishes. Let us define such a set of activities by Sk. That is, Sk is the set of activities that start after activity AK finishes. So the top-down greedy approach is shown in this pseudocode. It takes as input the list of starting and finishing times of the n activities and the index k for the subproblem Sk that it has to solve. We can understand this by visualizing its execution on our example. We begin with a dummy activity denoted by A0 that finishes at time 0. So the first activity that follows would be A1 that starts at time 1. And then we look at A2. Since A2 overlaps with A1, we do not consider it. Then we look at A3. Since the finish time of A1 is greater than the starting time of A3, we again ignore A3. Then we look at A4. Since the starting time of A4 is greater than the finish time of A1, then we can include A4 in our schedule. Next, we look at A5. And since A4 overlaps with A5, A5 is neglected, same as A6 and A7. Then A8, which starts after the finish of A4, is included in the schedule. Then A9 is neglected, A10 is neglected, and the next activity included in the schedule would be A11. Therefore, in the end, we would have 4 activities within this schedule. So the procedure for the activity selection problem was a recursive approach. As an exercise, try to work out an iterative version of this procedure. The last example that we will be solving today using greedy approach is a coding problem called Huffman coding. Huffman codes are used to compress data in an efficient manner. It works by using the distribution of characters that appear in a file to be compressed. Using this distribution, it compresses the characters using codes that take up much lesser space in terms of memory. As an example, say you have a file with 100,000 characters in it. Let's say the characters used in the file are A, B, C, D, E, and F, and their frequencies, that is the number of times they appear in the file, is given in this table. So A appears 45,000 times, B appears 13,000 times, C 12,000 times, D 16,000 times, E 9,000 times, and F 5,000 times. So the sum of all this would be 100,000 characters. Each of these 6 alphabetic characters require 8 bits to be represented. What Huffman coding does is that it represents each character by using a binary string of zeros and ones known as code words. These code words, however, will require lesser than 8 bits and thus can save the file in a compressed form, taking up lesser memory. So going back to the 100,000 character file we saw in the previous slide, we would require 800,000 bits to save the file if no compression technique was used. Now, given just the 6 characters, that is A, B, C, D, E, and F, we can represent them using 3 bits, since 2 to the power 3 is equal to 8, and we need only 6 unique binary representations. Say A is represented by 000, B by 001, C by 010, up till F, which can be represented as 101. So 3 bits for each character. Therefore, for 100,000 characters, it would take 300,000 bits of storage, which is a compression of approximately 62.5%. In this compression technique, each character has a code word of fixed length. It means that every character uses exactly 3 bits to be coded, irrespective of their distribution in the file. This type of coding is called fixed length coding. But is there a way to further compress the file even more better? The answer is yes, and it can be achieved by using variable length code words instead. This approach requires knowledge on the frequency of each character in the file to be compressed in order to outperform the fixed length coding approach. The trick here is that it allocates the characters that appear more frequently with shorter keywords and characters that have a low frequency with longer keywords. In our example, we see that the character A appears 45,000 times, which is more than the other 5 characters. So we give it the shortest code word, in this case, 0. Then character B with frequency of 13,000 is given the next short keyword, which is 101. And we keep doing this until we reach character F, which appears only 5,000 times in the file. So it gets the longest keyword, which is 1100. With this variable length coding for the 6 characters, we would require only 224,000 bits to save the file. This corresponds to a 72% compression, which is far better than the fixed length coding alternative. The code words being allocated in the variable length coding approach, however, cannot be done randomly. Only those code words can be used that are not a prefix of any other code word. Such codes are referred to as prefix codes. So, if you use prefix codes, the variable length coding will always guarantee optimal compression as compared to any other character coding. For instance, coding ABC using the table that we saw earlier would actually give us 01011100. The question that arises is, why do we prefer prefix codes? We will see shortly that using prefix codes actually makes the decoding process very easy. Now, can you tell what does the following binary sequence decode to if we use the variable length coding approach? Using the table that we saw earlier, we would get AABE. Prefix codes can be represented as binary trees, where the leaves represent each character in the file. If we interpret a left child link to be coded as 0 and the right link to be coded as 1, we can represent our example using the following binary trees. The left tree is for the fixed length coding, and the right tree is for the variable length coding. The circular nodes in the middle of the tree actually denote the sum of the frequencies of the leaves. So 45 plus 13 would be 58, 12 plus 16 would be 28, and the sum of these two would be 86, and so forth. Another interesting thing about Huffman prefix coding is that for any given file of characters, the optimal coding will always represent a full binary tree. That is, each non-leaf node will have 2 children. Huffman came up with a greedy approach to construct these prefix codes, which we call today as Huffman code. The pseudocode of his greedy approach is given here. As input, the procedure Huffman takes the set C of n characters in the file, where each character has an attribute called C.frequency, which is the number of times the character appears in the file. It then puts the set C in a min priority queue denoted by capital Q, which upon calling the function extract min always returns the character with the least frequency in the queue. In the for loop, it creates a circular node, places the least frequent character as the left child, then the next least frequent character as the right child, and the sum of the frequencies of these 2 children as the parent circular node. In the end, it returns the root of the tree, which contains the total sum of the frequency of all characters in set C. Note that the Huffman procedure builds the tree in a bottom-up manner, as it starts by merging the leaves that have least frequencies and then moving up till it reaches the root. So, for a set of n characters, it requires only n-1 merging operations, which is done in the for loop on line 3. Returning back to our example where we had 6 characters, this greedy pseudocode will require only 5 iterations of the for loop for building the binary tree. Now, let's apply the Huffman pseudocode on our example. We list down the characters in the increasing order of their corresponding frequencies. Remember that these characters will always be the leaves of the binary tree and will never appear as intermediate nodes. Since F and E have the lowest frequencies, we merge them under a circular parent node and put the sum of their frequencies, that is 5 and 9, as the key of the parent node, which is 14. Sort the list again. Now we have C and B at the beginning of the list. So we merge C and B. Doing so gives us figure C. Again, we sort the list. Now merge the circular node of value 14 with leaf D. Sort it to get figure D. Keep doing this until all the nodes are merged into a single binary tree. From this tree, we can now easily obtain the prefix code for each character, starting from the root and going down the path until we reach the character of interest. So if we are looking for the code for character A, we start from the root and we go to A. So the code would be 0. Similarly, the code for B would be 1, 0, 1. The code for F would be 1, 1, 0, 0. And for E would be 1, 1, 0, 1. Observe carefully that no code is a prefix of any other code in this greedy approach.